By the way, you guys can see whether I'm recording or not, and I rely on people like Jeremy and stuff to just say, "Oh, Professor Brown, don't forget to record." Of course, that happened yesterday. I lost about the first 10 or 15 minutes of one of the classes because I thought I had started, but it just didn't come on. And someone says, "I don't think we're recording yet." Now, this is the schedule. This is printed. This I sent to you. This is part of the syllabus. We will never deviate from this. I know exactly how long I need to spend on each topic all semester long. And so this is critical that you understand where we are, not just the topics, but also the dates. Now, I've gotten a lot of emails about the textbook. So I want to show you, I spent over 3 years with Professor Tan developing this book. It was a labor of love on his part. Okay, this is Tan Volume 2. All right, this is Tan Volume 1. They both have the train thing on the front. The first edition, which came out many, many, many years ago, isn't very different from the second. So if you didn't want to spend the money on the second and you wanted to buy the first, you can probably find it for very cheap. Someone told me yesterday they just bought it on Amazon for under 50 bucks. But the thing is the new edition, again, it's been over 3 years in the making. The new edition, he's practically giving away. Okay, I'm not getting anything from this. But the ebook, he's making available for $49, the hard copy for $89. Now you have to understand, if you bought a brand new calculus book, I haven't seen a calculus book for under $300 in the last 20 years. That's normally what it would cost. He's selling it pretty much at cost because he wanted to do this for Mesa College. We've been working together for a while. He's retired. He doesn't need the money, but he really enjoyed this. So I don't care what book you have. And in fact, if you use a different textbook altogether, that's fine. But I think this book is easier to follow, and I'm going to be using it for the next few semesters. Okay. Now, by the way, in general, don't do a lot of chatting because I can't always see the chats. I'm too far away. Plus, they only stay on the screen for about 3 seconds. But someone said something about the ebook. If you buy the ebook, I believe the ebook is $49. The hard copy is $89. If you buy the hard copy, you get the ebook automatically. So that's a really nice deal. And the other thing is Professor Tan did, if you buy the ebook and then later you want to upgrade, you just pay the difference. And the reason he did that was because for those of you who are in my class, or I'm sorry, I should be talking to the Calc 2 people. Last semester in my Calc 1 class, the book hard copy did not come available till about the middle of September. So that means everybody had to start with the ebook. So he allowed them to simply upgrade if they wanted to. I am not a fan of ebooks. Okay, I absolutely hate the concept of an ebook. I spend way too much time already in front of my computer, and that's not a joke. I mean, all the writing I do, I spend 1 to 2 hours a day answering emails. If I actually had to do my calculus by staring at the computer screen in addition, okay, I don't like ebooks because it means I'm stuck in front of my computer to do anything else that I'm doing. I like to take a book and I sit outside in my patio. I have a fireplace out there. I kick back, maybe a glass of wine if it's, not terribly difficult math. I'm joking, but I don't like doing my work in front of my computer in addition to all the work I do in front of my computer. If you're okay with that, then the ebook's the best deal in town. But if you'd rather not be stuck to sit in front of your computer anytime you do the math, then the hard copy is kind of a nice alternative. Now, in addition, on the schedule, I want to make sure everybody understands. There are exactly 26 lectures throughout the course. We meet 32 times. There are 26 lectures. There are 26 quizzes. There's a quiz for each lecture's material, okay? And the quiz will mirror the lecture. Those who've looked at the first quiz, you can see what it's about, and that's basically what we're going to be talking about today. The quiz is always due 2 classes after the lecture, okay, 2 lectures later, which means that if there's a holiday or an exam, that would extend, okay, to make it an additional amount of time. But you always have a minimum of 7 days to do a short quiz that is based on the lecture. You're supposed to get the quizzes correct. You're supposed to get A's on the quizzes because you will have had a week to practice similar problems in your textbook and then get really, really good at them and then try the quiz and then nail it. Every question I ever ask you, I will have already done in class, by the way. I will have done numerous versions of that question. Attendance in this class is not on whether you attend the Zoom lectures, because I said the lectures are optional. It's wise to attend the lectures, but you're not required. So the attendance is measured on simply, did you turn in what was due that day? Starting a week from today through the final exam, there will be something due every class, either a quiz or an exam. So failing to turn something in would be counted as an absence. So it makes it real simple. Just turn something in. Is that, you know, it is reasonable to say that every person in this class is going to have at least one day where they just couldn't get to the stuff in time. You know, everything happened that same week. You had 3 exams, you had a paper due, you had all these things, and you didn't get to the quiz that week. Okay, that happens. I get that. So then just turn in a blank quiz. Right? Why be absent? When people don't turn in quizzes, they don't pass. That's a really simple thing, because it means they're not doing the work, they're not keeping up. And the quizzes, again, are a quick check. Now, when people say, well, how much work should I be doing? This is calculus. The traditional rule of thumb in calculus was always 3 hours outside of class per unit. Now, the overall governing college rule, most of you probably learned early on, is the 2-to-1 rule, is you generally expect to spend at least 2 hours outside of class for every hour a class meets. But there are classes that you've taken, you know, GE classes, that maybe the outside work is so minimal, it's not even 1 hour per unit. And then you've had classes like physics. Professor Mona will tell you on day 1 of Physics 195 that if you spend less than 30 hours, you are not even going to pass the course. That's an absolute rule in physics. 30 hours is the minimum to pass. It's a 5-unit class. That means 6 hours. Yeah, everybody knows that. Calculus 3-to-1 is probably a safe rule. So if you're not spending a significant amount of time practicing problems, then it's going to be really hard to get good at this. You see, there's a game that's going to be played this Sunday between a couple of teams down in Tampa. And I'm pretty sure they're all going to show up to the game having practiced for many hours. They're not going to just show up to the game. So it'd be like saying, I'm going to just show up to an exam not having practiced any of the mathematics. That probably won't go entirely well. So how many problems do you have to do in a section? Well, simple. You have to be able to do every single problem in your math book related to that thing. Do you have to do every problem? No, you have to be able to do every problem. So I say in the syllabus, start by doing every other odd problem. Now, I say the odds because they generally have the answers in the back of the book. And if you're consistently right, then you're probably good. If you're not consistently right, then throw in a few extra problems or get help. But when we're going over a concept, if you're not going to practice it, you're not going to get good at it, because there's too many variations and there's too much understanding that takes place. Now, at the bottom, you see all of the key dates. Those are not going to change. So be mindful, you know, those are the things that should go on your calendar. So we're going to start right off with the concept of limits. Limits, I remember as a math student, just kicked my butt. That it was so abstract, and I was so good at number crunching, and numbers in algebra came so easy to me that the concept of a limit just, it fried my brain. If you're thinking of numbers, think of the real number line. You know, I just said, what's the first positive number? Starting with 0, what's the first positive number? There isn't a first positive number. So, because no matter what number you tell me, I can cut that in half and you're closer to 0, and then I can cut that in half and you're closer to 0. I can keep getting closer to 0. There is no first positive number. So things like that just were very confusing to me at first until I realized what's happening. A limit is the destination. It's not where you are. So the concept of a limit is, let's keep it really, really simple. If I had a function, let's say f of x equals 2x. Let's start with something really, really simple. Okay. Well, there's nothing strange. This is just a line. This is pretty simple to interpret. If I said, what is f of 3? You'd say that's 6. Okay, there's a point. Let's say it's right here, 3, 6. That's a point on the line. So as I am getting closer and closer and closer to 3 on the x-axis from either direction, my y values are getting closer and closer and closer to 6. And in fact, when x is 3, y is 6. Beautiful. But the functional value is 6. The limit is, where am I headed? I don't ever actually get there. Just where am I going? I can see it at the end of the street. I want you to go to that place as you get in your car. That place that I want you to go to, that's the limit. Now, when you get there, it might be gone. It might have been, a mirage or something. Have some fun. So the way we say it, the mathematics, we write it like this. The limit, LIM, this is one of the few times people tend to use cursive. The limit x arrow means approaches. The limit as x approaches 3 of f of x is 6. As I get closer and closer and closer, I'm headed towards 6. Whether I get to 6 or not, it's not even relevant. I know that kind of blows people away, and I'm going to show you several examples. So it's partly the notation that we use. So limit, underneath we write x approaches. So right off the bat, I'm introducing symbolic notation to you. Arrow means approaches, never reaches. I'm approaching 3. I'm not asking you to plug in a 3. I'm saying as I approach 3. Get closer and closer and closer and closer and closer. Now, a lot of people like teaching this using a calculator and say, all right, insert values that are really, really, really close to 3 and then look at it that way. Nah, that's not a very good way of looking at it. Just as I get closer, I can see the point, that's where I'm going. I'm approaching 3, therefore my y value is approaching 6. And if the y value is approaching 6, then the limit is 6. Now, let's totally mess up your mind here. Now, going back to baby algebra. If I said f of x equals x squared minus 1 over x minus 1. If I asked you what is the domain of this function, and this is critical, this is part of the reason I needed you guys to watch the videos to review things like domain. How do you find a domain? What is the domain? Now remember, the term domain, it's not a variable. Domain is the set of all possible inputs. What values could I use? You see, I'm calling it f of x. What if I called it f of t and I use t's, or I called it f of q and I use q's? The domain is the same. The domain is the set of numbers. The domain isn't a variable. So a lot of people say, oh, domain is the x. Well, only if x is your input. So domain is what could I input? And I think it's safe to say you can put in any real number except 1. Okay? So let's write that down. So my domain is all real numbers except 1. And the easiest way of saying that is with an interval. Negative infinity to 1, union 1 to infinity. That's the same as saying instead of real numbers, removing the number 1. So some people write it this way. This is another notation. The set of real numbers, the backslash is actually means remove or delete. Some textbooks will actually use a subtraction symbol. The number 1. The set of real numbers, removing the number 1, or just simply saying that. We all agree that was simple enough. So now here's the question. Can you reduce this? Well, the numerator clearly factors as x plus 1, x minus 1. So I can cancel factors of x minus 1. And that would give me simply x plus 1. So my function is equal to x plus 1. Well, not exactly. You just said the domain of this function is all real numbers except 1. And I could reduce this to this. I cannot all of a sudden now have 1 in the domain. 1 is not in the domain here. 1 still is not in the domain here. So in remedial algebra, you may not remember this, but in remedial algebra, what we did at this point was we threw in a disclaimer. This quantity here is identically equal to this quantity here as long as x is not equal to 1. How come? Because 1 is not in the domain and it's still not in the domain. There are very few absolutes truly in mathematics, but one of the few and one of the easiest ones to remember, is the domain cannot change. The domain of the function is what we said it is. It can't change just because I started manipulating the function. The domain is still all real numbers except for one. Okay. So this is so much easier to work with than this. So now if I said graphically, if I asked you to graph this, this would be very tricky. And if I started plotting points, I'd see decimal values all over the place and it'd be really confusing. But instead, what if I said, let's just graph this? Well, the line y equals x plus 1 simply looks like this. Oh, okay. So is the graph of this the same as this? Well, almost. Remember this statement? Oh, so if I go 1 right about there, I'm going to put a hole. And this would be the most appropriate graph that represents this function. I have a hole. I removed a point. And by the way, what point did I remove? I removed the point 1, 2. How do I know that? Because the line y equals x plus 1 passes through the point 1, 2, but we can't have x be 1. Therefore, we can't have a y value of 2 either. This graph will never have a y value of 2 because I can never use an x value of 1. This is the way we tend to represent it, the little hole. Now, if I did this on my graphing calculator, or if I did this using Desmos or any computer technology, I'm not going to see the hole. It's going to look like the line. And the reason is we're removing one point, but a point is infinitely small. It doesn't take up any space. So we wouldn't actually see it visibly if we remove the point. So that's why we represent it this way. That point that I removed is called a removable discontinuity. I removed it from the graph, but it was only one point that I removed from the graph. Okay, is everybody cool with that? I removed one point. So okay, this is not complicated. We did this stuff in pre-calculus. We understood this pretty well. Great. We agreed that this function and this function are identical at all real numbers except at 1 because 1 isn't in the domain. So now here's the question. I would like to find the limit as x approaches 1 of x squared minus 1 over x minus 1. Well, that's a problem because f of 1 does not exist. There is no f of 1. 1 is not in the domain. So that could be an issue. Well, we're going to look at our algebra and see what happens. So, common sense. I'm cruising along from either direction, and as x is getting closer and closer and closer and closer to 1, clearly the y value is getting closer and closer and closer to 2. As I'm moving down the road, and I get, there's the address where x is 1, and when I get there, guess what? There's a crater. There's a big hole. There's nothing actually there. I can't physically get to where the point is, but I know where the point is. I can see it. The point that I'm interested in is the point 1, 2. But since x never equals 1, y never equals 2. But as I'm heading towards x equal 1, clearly the y values are headed towards y equal 2. Therefore, the limit is 2. The limit exists even though the functional value does not. I know it sounds kind of crazy, but here's what we do. We say this quantity, therefore, is equal to, let me erase this here. We said that this quantity is equal to this quantity for all real numbers except 1. Therefore, the limit of this quantity should equal the limit of this quantity because they are equal for all real numbers except for 1. And remember what I said here? This says x approaches 1, but never reaches 1. Approaches, never reaches. So as x gets closer and closer and closer and closer to 1, x plus 1 is getting closer and closer and closer to 2. Therefore, the limit is 2. X is approaching 1, y is approaching 2, so the limit is 2. 2 is where I would have got to if I could. This is what a limit is. A limit and the functional value do not have to be the same thing because in this case, there is no functional value. And again, right, that's a mind blower the first time you think about it. but it means I can get as close as I want. How close can I get to 1? Infinitely close. Now, if you thought about it from a numerical standpoint, I can get to 0.999999999 or 1.000000001, right? And my y values would be so close. But that's really a complicated way of looking at it. Just do it from an algebra point of view. So the rule of a limit right off the bat is 1 is the only number I'm never going to use. So algebraically, this quantity is equal to this quantity for all real numbers except for 1. That's why I can say the limits are equal. And then I can evaluate it. So the rule for limits in general, if you can evaluate the limit, then you evaluate the limit. You just plug in the number. If it turns out there's a hole there, then you might have to manipulate it algebraically just a little bit. So let's try another one of these guys. Okay, a removable discontinuity is the most common type of limit we work with. There are other types. This is our favorite one because it's the most interesting, and algebraically it's probably the least challenging. We're going to work with trig limits and all sorts of crazy things. Vertical asymptotes, horizontal asymptotes, slant asymptotes, everything under the sun we're going to go over at some point. So this is a good starting place. Okay, what if I had something like this? I want the limit as x goes to, let's say, 4 of the square root of x minus 2 over x minus 4. Now, I said before, if I can evaluate the limit, if I just said the limit is x goes to 13, x goes to 27, x goes to 1, I could just evaluate this. There's nothing weird happening. Weirdness is only happening when x is 4. The only weirdness is anything that would make my denominator 0. We agreed that would be weirdness. So any number that I asked you to approach, you could just plug it in because the functional value would exist. And if the functional value exists, go back to this one here. I said the limit as x goes to 1. What if I picked any other number on the number line? That would have been easy. You just plug it in. Evaluate, because there was nothing strange going on. But this is calculus. We are far more interested in the strange. That's way more interesting, and that's where things come from. Things don't come from the easy, they come from the strange. So I'm going to show you some notation that I want you to get used to, because this notation does not change for the 3 semesters. Now, this is something I make a serious point about. I teach all 3 semesters. The one thing I do not want to do later on is say, okay, remember how we did it in Calc 1? Now we're going to do it differently. Remember the notation we used then? Now we're going to use different notation because that notation really wasn't very good or wasn't clean. No, I'm going to teach you everything you need to know for the next class and the next class and the next class. And from a notation standpoint, I don't ever want you to have to change the way you do things. I taught remedial algebra at Mesa College for many years, Math 46, and I found it very interesting that the textbook we used for many years gave different exponent rules. Within the same textbook, they changed the rules of how to deal with exponents every time they showed you something new. And each time they'd say, okay, remember what we did before, scrap that, here's the right way to do it. There are 5 different versions of the same formula. I'm going to give you an example. This is baby algebra. X to the A over X to the B. In baby algebra, they say it equals x to the a minus b. We know that is true. But in baby algebra, it says it's only true if a and b are both positive integers and a is bigger than b. This is the first rule in every algebra book, including the one we've been using at Mesa for years. This is only true if a and b are positive integers and a is bigger than b. Now, you know that statement is absolutely incorrect in every conceivable way. So then later, when they introduce what a negative exponent is, now a doesn't have to be bigger than b. You see, if I said x squared over x to the 5th, well, heck, I can cancel. I know I'm going to get 1 over x to the 3rd. That's not really a question. The algebra book says this is an impossible question until the next chapter. And then it says, okay, now you can do this. But only if they're positive integers. Then it introduces eventually negative integers. And then later when they introduce roots, then they introduce fractional exponents. And then later when they do logarithms and they introduce exponents that are real. The funny thing is, this rule is true whether a and b are numbers or not. If I said x to the question mark over x to the exclamation point, that is equal to x to the question mark This is true no matter what these are. This is an absolute mathematical rule for every conceivable scenario. But in the algebra book, they present it 5 different times and they change the rules each time. And only in the last presentation is it actually correct. So students have to keep relearning the same rule. That's a bad way of doing anything. So in calculus, we're going to learn things one time, and we're not going to say, now later, let's change that. No, we'll expand on that. So the notation I want you to use, if I can evaluate it at 4, I'm going to evaluate it at 4. But if I put 4 in here, I'm going to have 2 minus 2, which is 0. If I put a 4 here, I get 4 minus 4, which is 0. Now, don't write this. This, do not put equals. This makes no sense mathematically because 0 over 0 isn't a number. 0 over 0 isn't an anything. 0 over 0, I'm going to give you a name. These are one of the most studied things. It's called an indeterminate form. There are exactly 6 indeterminate forms that we're going to learn in calculus. We're going to learn 2 in this class and then 4 next semester. An indeterminate form is the form that your quotient or your function is taking on if you actually try to evaluate it. 0 over 0 isn't a number, it's a form. So what we do is we don't say equals. We say this quotient is approaching, and we actually use brackets. We say this is a form that we are dealing with. This quotient approaches this form. Again, 0 over 0 is not a number. Remember in the last example, we did x squared minus 1 over x minus 1. Had we evaluated that at 1, we would have gotten 0 over 0. Oh, but then that meant we could factor and cancel. So the vast majority of the time, when you have this indeterminate form right here, ultimately you're going to be able to factor and cancel if it's algebraic. Trig is something else, but this is an algebraic statement. I am eventually going to be able to factor and cancel. And what exactly am I going to factor and cancel? The x minus 4. I call that the problem child. If I had asked you any number other than 4, this would not be an issue. But I asked you the only number that made it an issue, and that's why it's remotely interesting. I am not interested in the graph, but I am a big fan of after the fact producing the graph, because sometimes after you do all the algebra, looking at the graph after the fact and you say, ah, I see what I just did. But you can never get the answer from the graph. And more often than not, the graph is more complicated than the algebra anyway. So in this case here, since this is of the form 0 over 0, it's this particular indeterminate form, I want to know, is there anything I can do algebraically to clean this up? Yeah, it turns out I can. I need the x out of the root. Now, some folks will say, well, square it. No, squaring it won't work. That'll just make it more complicated. And you can't square something and say it's equal. No, that won't work. Instead, what if I multiplied numerator and denominator by the same quantity? Then I can say it's equal. In fact, what quantity would I choose? How about the conjugate? Again, if you watch the videos that I posted, I talk about things like using conjugates. I know that no matter what I say next, it's still going to be true because I ultimately multiplied by 1. Root x plus 2 over root x plus 2 is equal to 1 for every value of x that you could use. But when I do this, I now have the limit of, on top, I have x minus 4. On the bottom, I still have x minus 4, but now times root x plus 2. I distributed on top because I wanted to get the x minus 4. Notice I did not distribute on the bottom. And the reason I didn't distribute on the bottom is I want to cancel that factor. If I distributed on the bottom, I wouldn't be able to see the canceling. So clearly. Now, right now, do a quick check. My numerator is still approaching 0. My denominator is still approaching 0 because they both still have a factor of x minus 4. But like in the last problem, okay, what am I left with? So here's, in simple English, here's what we're saying. This quotient that we started off with, where 4 is not in the domain, is identically equal to this quotient, as long as x is not equal to 4. Again, 4 is not in the domain, but these two are identical for all real numbers in the domain except for 4. But the limit says I'm going to approach 4. I'm never going to actually get to 4. I'm only going to approach 4. So now I can say, aha, I can evaluate this quantity. So the rule of thumb in general for limits is, if it's an indeterminate form, you must manipulate it. You can't evaluate it. You have to manipulate it. But after you manipulate it, like we did here, if you can evaluate it now, you do, and then that's going to be your answer. There's no way I can look at this and see what the answer is. But now when I look at this, it's easy to see what the answer is. As x gets closer to 4, this quantity is getting closer to 1 over the square root of 4 plus 2, which is 1/4. So the limit is 1/4. You notice I've evaluated the limit. I don't write limit anymore. Once I evaluate the limit, I'm done. So there's some simple rules that a lot of times you're not told till much, much later in the process. Sometimes people don't even show you this till second semester. But I like you guys to know things right off the bat if humanly possible. I know this is day one. Limits are amazing things. You can do algebra with limits that you cannot do in other areas, and we're going to prove some of the rules over the next couple of days. But here's the bottom line test to know if you did a limit correctly. If I cover up the word limit, just cover up limit, then is this quantity equal to this quantity equal to this quantity? Not the 1/4. Is that quantity equal to that quantity equal to that quantity? Yes, I know algebraically I can manipulate those. I know that x equals 4 is not in the domain, so x equals 4 is still not in the domain, but I know algebraically that quantity equals that one equals that one. Therefore, the limit of the quantity is equal to the limit of the quantity is equal to the limit of the quantity. As long as you're saying the quantities are equal, then the limits of the quantities are equal. And since x never actually equals 4, taking the limit here is totally legal, because now I can. Now that, again, it can be mind-boggling, okay? But the algebra of limits is just not that bad, okay? It's not that terrible. We're going to work with infinities very, very soon. And it starts getting a little more tricky. Now, I'm going to ask a question, and then we're going to figure out how to attack it. Now, one of our least favorite types of problems to deal with in calculus is something called a piecewise function. A piecewise function is one where I cannot just say f of x is, I have to tell you the function in pieces. So let's start with a really simple one. F of x is equal to the following. It's equal to x when x is greater than or equal to 2, and it's equal to x squared when x is less than 2. So right now, if you stare at that, you realize the domain is all real numbers. Okay? The domain of this function is all real numbers. In this case, I want to draw a graph because I'd like to see what this looks like. All right, so y equals x, but not until x is 2. That'd be about right there. And the other piece is y equals x squared. But when y is x squared, then I'm going to be about right there. That makes it fairly accurate. Okay? And do a quick check. When x is 2, y is 2. But on the other side, if x were 2, y would be 4. But notice I have a hole. I don't know if that's obvious. Let me do that a little bit better. I have a hole right there. Why do I have a hole? Because it says less than 2, not less than or equal. So I never get to 2 on the parabola, and then I pick up here. So here's the graph. This is not a complicated function, but it is most definitely a piecewise function. So if I asked you for the limit, okay, this is not a complicated thing. But again, I want to show you good notation so that there's no chance that you misinterpret. So if I said, what is the limit as x approaches 5 of f of x? Well, if I'm approaching 5, then I'm going to be approaching it along this graph. See, as I'm approaching 5, because this graph never gets to 5, so I'd be approaching it here. So that would be the limit as x approaches 5 of x. Now, as x approaches 5, y is clearly going to approach 5. What if I asked for the limit as x approaches -2 of f of x? Well, then I would be approaching it along this curve because -2 is over here. Oh, I would not be using the line, I'd be using only the parabola because -2 is part of the domain of the parabola. So I would say this is equal to the limit as x approaches -2 of x squared, because that's the graph I'd be on. And that clearly would be 4. So to illustrate that, there's -2 comma 4 right there. And over here, there's 5 comma 5 right there. This is pretty easy. If I'm moving along a piecewise function, I just got to figure out which piece I'm moving along. So how could this ever be complicated? Is there any question that I could possibly ask that would even be interesting? I think there's one. I think you guys probably figured out what would be the interesting thing to take the limit of. Oh, I don't know. How about we take the limit as x approaches 2? Now we have a problem. Because if I'm approaching 2 from this direction, then y is going to be approaching 4. But if I approach 2 from this direction, then y is approaching 2. I got a problem there. Because my graph has a break there, how do I ask this question? So this brings to one of the really important rules of limits, okay? And that is limits have to be the same from both directions. So a general rule is this. I'm going to write it like this. For the limit as x approaches a just being any value, of f of x to exist, the limit as x approaches a, I'm going to put a little negative sign up there and explain what that means. That means from numbers to the left of a. That means numbers to the right of a. So in simple English, for a limit to exist, the limit from the left must equal the limit from the right. Okay? In this case, my a would be 2. It doesn't matter what value I picked. So I would have to have the limit from the left equaling the limit from the right. So I'm going to show you how you write that notationally. I think we all agree that I'm approaching from 2 different directions. So that is clearly a problem. So it's kind of like this. All right, I ran into an old friend yesterday and I said, hey, remember when we were kids and we used to play down by the railroad tracks and we'd throw rocks and, you know, let's meet tomorrow for lunch down by the same place at the railroad tracks. So we do this. We're coming from different parts of town. But unfortunately, overnight, there was a massive 8.0 earthquake and, you know, so the railroad tracks got separated by 100 yards. So I showed up to my place on the railroad tracks, and my friend showed up to their place on the railroad tracks, but we're about 100 yards apart. So in other words, the limit from one side did not equal the limit from the other side. It doesn't matter what the functional value is at all. F of 2 is 2. But the limit from the left and the limit from the right are going to clearly be different. So let's go ahead and I'm going to write this down. So I'm going to write the limit as x approaches 2 from the left of f of x. Now, if I'm approaching from the left, that means I'm approaching it along the parabola. So that will equal the limit as x approaches 2 from the left of the x squared graph, which we know is 4. How about if I said, let's do the limit as x approaches 2 from the right of f of x? Well, if I'm approaching 2 from the right, then I'm approaching along this graph. So that would be the limit as x approaches 2 from the right of x, and that is 2. These values are not the same. So our conclusion, and this is notation again that you may or may not have seen. Different color for emphasis. D, N, E. Does not exist. I asked a limit question. There is no answer to this question because the limit does not exist. Okay, and it's very important that we understand that. I've made a very simple graph. So the illustration is really, really easy to follow in this case. The limit from the left and the limit from the right are not the same. Now, in the first couple of examples that I did, we didn't consider left and right-handed limits. We didn't need to, because all we did was pluck one point off the graph. The graph looked like this. We just removed a point. We had a removable discontinuity. Okay. In this case here, it wasn't a removable discontinuity. So now, I'm going to ask you guys a simple question, and I want everyone to think about this for a moment. Same question. I want to know this. Is there anything you can do to my original function? You can do one thing only. Is there anything you can do to my original function so the limit does exist? So I'm going to give everybody a moment here. I want you to think about it. Okay, and I'm going to go ahead and go to the gallery for a moment. If you think you know the answer, just wave at me. Yeah, I wave for a moment because I got two screens. But what I want to know is there any tweakage you could do to my original function that would make this work? So give it this way: make the limit from the left equal the limit from the right. Now, most of you don't have pictures, but if you think you got to, just give me one of these. Okay, Pierce. Unmute yourself.
Oh, I have to answer in front of everyone?
Yeah, then you get to rejoice, celebrate, do the happy dance, you know, king for a day, all that kind of stuff. What do you think?
I would imagine it would be take the square root of the x squared in the original piecewise function.
Well, but if I take the square root, oh, you're saying replace this with x.
Basically.
Oh, I see what you're saying. Oh, okay. You said if yeah, that's more complicated. Let's just call it x. So Pierce says, if we make this be x, then it's just the line y equal x. That would work perfectly. Okay. Does anybody else have a thought? Like I said, there's more than one possible answer.
Is it possible if we like shift the perspective, like we only look at the negative, like the left-hand side, where it's like a continuous function?
Well, okay. By him calling this an x, he made it continuous. I want to, okay. By the way, that's the right word. I want to avoid it because we're not going to define continuity for another week. So I'll avoid using that word. but you're right. I want you to perhaps look at these you can't really do much with, but tweaking one of the original functions. So making this an x was one thing. Does anybody see anything else? See, I would really like these to meet.
Shift dx squared up.
I'm sorry, say that again.
Would we be able to shift the graph upward?
Okay, be more specific. How exactly? Do you want to shift this one upwards, or do you want to shift this one downwards? Or do you want to shift this one upwards or downwards? You're on the right track. So exactly what would I do?
You would add 1 to x to make it equal to x squared, or 2.
2. So if I make this x plus 2, does everyone agree that that would work? This got shifted up to, this one would be 4. Well, what's the other thing I could do? How about
-2?
-2. Beautiful. So does everyone see, I like the word you used. Shift was a great word. If I shift either of those two graphs 2 units, I could make them meet. So although the original problem failed hopelessly, they didn't meet. If I shifted one of them, or in this case, one of the suggestions was simply change that function, that would have worked. By the way, could I have made that an x squared? I said there's more than one option. So that's what I wanted you to see. Sometimes it sounds weird and sounds very corny. It's the whole thinking outside the box thing. It failed because, so what would I have to do to fix it? Okay, so go ahead and mute yourselves again. So the concept of a one-sided limit, okay, it's a little bit tricky. So I'm going to show you a couple more examples of that. The notation is not tricky, but it's notation you may have never seen before. So the concept of, if I put a number on a number line, there's only two ways I can reach the number, from this side or from this side. When we get to 3 dimensions, when you do this problem in Calc 3, then it's really crazy. Right now, there's only 2 ways I can approach a number. But if I'm in 3D, there's an infinite number of ways I can approach a number. So all of this stuff changes, a little more complicated later on. So the concept of a one-sided limit means I'm only approaching from one direction. So the original question might have been something like this. What's the limit as x approaches 1 from the right of x squared plus 3? Now, there's nothing weird going on in this. There's no holes, there's no nothing. Can I simply just replace this with a 1? Yes, I can. The limit as x approaches 1 from the right means x is approaching 1 from numbers bigger than 1. If it helps, it's approaching 1, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.5, 1.1, 1.01. It's getting closer and closer to 1 from numbers bigger than 1. This limit is clearly just 4. Okay, so here's my next question. What is the limit as x approaches 0 of the square root function? Now I want you to think about this for a moment. I don't need a graph. I don't need a graph for this. Although it is useful to know that the square root function looks like this. The domain of the square root function is non-negative numbers, so 0 to infinity, including 0. Yes, you can take the square root of 0. That's not an issue. So, anybody think they know the answer to this one? You can just go ahead and blurt it out. I won't even care who said it. Anybody think they know the answer?
I have a quick question, please, just regarding the one before the limit as x approaches 1 from the right here. How would that be any different if it was approaching from the left?
It wouldn't.
Right,
It wouldn't.
okay.
So I gave you one where nothing weird was going on just to show you that this doesn't confound things. It just makes you mentally think I'm coming from one direction. When will the direction matter? When something is piecewise.
Absolutely.
Or
Yep.
piecewise, it clearly matters because I'm defining things in this interval, I'm this function, in the next interval, I'm something else. And where the intervals change, that's where the left and right can be different. Now, I'm only giving you one function, but there's something goofy about this. There's something very goofy about this. I'm asking you the limit as x approaches 0. Now, one thing I want to emphasize, and this is not to be taken lightly, we are doing what is called real valued calculus. There is calculus of complex numbers. That's an upper division course that if you're an engineer, you will be taking in a couple of years. Real valued calculus means we are only considering functions whose input is real and whose output is real. Now, later on, when we talk about the hyperbolics, we're going to talk about complex numbers for just one day. That's the only part of the 3 semesters where we do complex numbers. But in general, we only are considering things that have real inputs and real outputs. Not that complex is evil. No. There's a few things we have to do. Calc 1 and 2 is we master the calculus of real numbers in 2 dimensions. That's what Calc 1 and 2 is. Calc 3 is now mastering the calculus of real numbers in 3 dimensions. And then as an upper division class, there's a course called complex analysis where you now master calculus of complex numbers. But you can't do the calculus of complex numbers until you have the calculus of real numbers down pat. So there's kind of an order of things. It sounds kind of scary, but it's along the path. If I put a negative value in here, we know we get an imaginary number. Therefore, negative values are not in the domain because they would produce imaginary results. Okay, and there's no imaginary numbers that we're going to work on in this case. So here's our dilemma. If I said, what's the limit as x approaches 0 from the right of the square root function? Well, that's pretty easy. I'm approaching 0 from the right. That's 0. Piece of cake. But what about the limit as I approach 0 from the left of the square root function? Anybody see a problem with that? There isn't any left. There's nothing to the left of the square root function. to the left of this is not in the domain. The limit from the left does not exist. It isn't 0. It doesn't exist because there is no graph to the left. So my overall limit here, this confounds everybody. But wait a minute, square root of 0 is 0. You're right. But the limit from the left and the limit from the right are not the same because only the limit from the right exists. Ah, okay. Now I'm going to make a simple sort of almost absolute statement. I love absolutes when you have them. You don't have a lot. One-sided limits. Okay, we did one of those. The limit did not exist. One-sided limits always exist though. So go back to the problem where we had the piecewise function. Both one-sided limits existed, they just weren't equal. One-sided limits always exist, except in one case. One-sided limits always exist unless they are outside the domain. The domain of the square root function didn't have anything to the left of 0. Therefore, that one-sided limit cannot exist. But in general, one-sided limits always exist as long as they're within the domain. So if I had asked any positive number any number other than 0 that's positive, that limit would have existed and would have just been the square root of that number. No issues. If I asked you to do the limit as x approaches 16, that limit would have been 4 because nothing weird is happening as I approach an x value of 16. It was only 0 that got weird because there's nothing to the left of 0. Again, that can be confounding. Here's one of those cases where I think the graph helps us understand it. The graph isn't the answer. The graph helps us explain why this is the case. Okay. Now, when it comes to answering a limit question, I want you to understand there's exactly 3 final answers to a limit question. Hang on one second. I'm running out of blue ink here. Grab a new blue pen. There's exactly 3 possible answers to a limit question. Okay. It can be finite. We've done a couple of examples of that. 6, -3/2, 0. It can be infinite. I believe that is next Tuesday's lecture. It says infinite limits. Those are very, very cool. Or does not exist. Those are the 3 possible results to any limit question. A limit can be finite, infinite, does not exist. That's it. Those are the only possibilities. And that throws people because sometimes we want to answer something else. No, most of the time when we're dealing with limits, we see things that are finite. But then later on, when we start talking about asymptotes and things, then we're going to see where the infinites come in. And we've already seen the D and E. D and E is not that complicated. D and E probably is the limit from the left and the limit from the right are not the same. That's probably where most D and E's come from. This was a D and E because there was no left-handed limit. So a D and E means, I probably have to look at the one-sided limits to make this work. Now, finite infinite does not exist if the answer is numerical, but a limit can be another function.
Can we manipulate this problem? Sorry for interrupting, but like if we shifted it.
This one, which I just erased everything. Which problem you referring to?
Sorry, the one we were just on where the one-sided limit, it didn't work for 0. If we say shifted it to the left, and then we evaluated it from the left side, would that be possible?
That's what I was just saying. I was just saying that if I had picked any number bigger than 0, any positive number, that limit exists.
Mm-hmm.
On the square root function, if you said the limit as x approaches any positive number, the left and right would both exist and it would just be the square root of that number.
Okay.
It's because I chose the end point of the function. Right, 0 is clearly the end point of that function. That's where it makes it a little bit tricky, a little bit more interesting. All right. So what if I have something like this? I've got the limit as x approaches a of x cubed minus a over x minus a. Oh, I'm sorry, x cubed minus a cubed. Now, it wouldn't matter what value of a I put in there. Now, I kept it fairly small. This is not complicated, but this looks a little bit tricky. As x approaches a, what form will this take on? Well, I'd have a cubed minus a cubed, a minus a. The only time you cannot evaluate a limit immediately is if your denominator is approaching 0. What if my numerator was approaching 0, but my denominator was approaching 7? Anybody want to tackle that one? My numerator is approaching 0, but my denominator is approaching something that isn't 0.
Would that be finite?
It'd be 0.
Yeah.
0 over 7. Yeah, if the numerator is approaching 0, but the denominator is not, then that limit is just 0. It's the denominator approaching 0 that really, sets the red lights flashing, saying, something strange going on here. But because they're both 0, we tend to think this is a factor and cancel. Now, the easiest way to do this problem is to simply factor this. It's a difference of cubes. Now, if you don't remember how to do difference of cubes, then you can always do synthetic division. But if I think of difference of cubes, it might make it a little easier. That would be x minus a, x squared plus ax plus a squared, squishing that in there. So that means that this is equal to x minus a times x squared plus ax plus a squared. I thought I just grabbed it. Did I grab? Oh, you know what? I grabbed a new blue pen, but now I'm using the one that's dying. There we go. Oh, there's some good blue. Now, I can't evaluate it yet. I have an x minus a in there. So I need to write it without the x minus a. And that means I have a squared, x squared plus ax plus a squared. Algebraically, this quotient is equal to this quantity always, except if x equals a. Okay? Because x equal a is the only value that is not in the domain of this quotient. X equal a is still not in the domain of this finished statement, but I'm asking what happens as x approaches a. And as x gets closer and closer to a, let's see, get rid of that. As x gets closer and closer to a, this is getting closer and closer to a squared plus a squared plus a squared. That's just 3a squared. Okay, that's kind of nice. It's kind of nice that we can do something like that. Now you see an a, you go, oh boy, oh, I got variables. No, a just represents any number. In this case, a is just any number, and there's my final answer. And that's just not that bad. Now I said, when you're doing a limit is not always going to be a number. In this case, we would think of this as a numerical quantity, but a limit can also be a function. How would I possibly make it be a function? Well, what if I have something of the form? Let's say we did something like this. I've got the limit as, how about a goes to 0 of x plus a quantity squared minus x squared over a. Now stare at that for a moment. You go, well, can I just replace a with 0? Well, if I replace a with 0 right off the bat, I got a 0 on the bottom, and that's already a problem. But I'd also have a 0 on the top. Now, that means ultimately, before I'm all done, I should be able to factor and cancel the a from this problem. Because if I have an algebraic statement and I have the removable discontinuity form, the 0 over 0 is the removable discontinuity form of the indeterminate form, then I should be able to factor and cancel, except I can't factor that. So what I'm going to do is expand. I'm going to go ahead and square this out. So this would give me the limit as a goes to 0 of. x squared plus 2ax plus a squared minus x squared all over a. Now, did I just make it better or did I make it worse? Well, stare at that for a moment. Does anything combine or cancel? I can't cancel a's because I don't have an a in every term, but I can cancel those guys. And now I'd have 2ax plus a squared all over a. Ah, can I factor and cancel an a now? Would that be possible? When it comes to doing the algebra, you don't ever want to skip steps, because if you skip steps, you might say something that's not true. But I'm a big fan of doing stuff like this. All right, let me factor out the a. Then I have 2x plus a. I'm just going to write it right over the top. So the next thing I write will be the factored and canceled version. I like doing, I could have done the expansion right on top. That wouldn't have been any problem with that. And so now this is equal to the limit as a goes to 0. Well, what's left? Looks like 2x plus a. As a approaches 0, what does that leave me with? Just 2x. So we just did a limit problem where my answer was not a constant, but it's still, in this sense, it's finite. How do you know the difference between finite and infinite? Well, if I see infinity as my final answer, then I know it's infinite. We work with infinities in calculus. We work with infinities all the time. I'm going to give you a simple example of something you may have seen in algebra and pre-calculus and so on. And this is a major, major piece of Calc 2 next semester. If I said, I'm going to walk halfway across the room, and then I'm going to walk half of that, and then I'm going to walk half of that, and then I'm going to walk half of that. A half plus a fourth plus an eighth plus a 16th, and I keep doing that. How long will it take me to get to the other side? You'd say, forever. Okay, let's suppose I have forever. If I have forever, will I get to the other side? Let's see, a half plus a fourth plus an eighth plus a 16th. If I add those up, they're getting closer and closer and closer to 1. Another way of thinking about it is the distance between me and the wall is getting less and getting less and getting less. The distance between me and the wall is approaching 0. Would you agree with that? Because I'm doing this. So if I said add up these numbers, a half plus a fourth plus an eighth plus a 16th, if I said do it a finite number of times, then I'm going to get a finite result that's less than 1. But if I said do it forever, do it infinitely many times. Really? Well, in pre-calc and in algebra, you did things like that. They called them infinite series. And I said, if I could do it forever, they would add up to 1. That's because I'm taking a limit. The limit is 1. I can't add forever, but if I could, the limit would be 1. I never actually get to the limit, remember? So if I'm moving around, now, one of my favorite examples to use for limits, okay, this is pure science back. Those of you who remember the Roadrunner Coyote, Wile E. Coyote and the Roadrunner, if you remember the Roadrunner cartoons were awesome. They did calculus all the time. And you don't have any idea how much calculus you've seen in your life. When we proved the fundamental theorem of calculus, which is considered maybe the most important work other than the theory of relativity in human history, I used the Star Wars garbage pit scene when the walls are closing in on Luke and the gang, because we actually proved the fundamental theorem. Yeah, they proved the fundamental theorem in the original Star Wars. You didn't realize that. But in the Roadrunner Coyote, if you guys remember, the coyote used to like to remove the manhole cover. There was always a manhole cover. He'd like to remove the manhole cover so that the Roadrunner would fall in. Now remember, they're not only on a 2-dimensional screen, they're moving in 1 dimension. They're moving on a line. So if I'm on that line, I technically can't see the hole. So the Roadrunner would be approaching the hole. That would be the limit. And then the idea he'd fall in. But the Roadrunner had the uncanny ability, if you remember, to move the hole. He could actually physically remove the removable discontinuity, which just is mind-blowing physics and abstract non-Euclidean geometry and all this stuff. But basically, It was always a removable discontinuity, the manhole cover, and the road runner, as he's moving along, cannot see the hole in front of him because he's moving at ground level. You don't see the hole until you literally are falling in the hole. Well, that's exactly the notion we're doing with limits. Where am I going? If I could actually get there, what would the y value be if I could get there? But in most cases, we're removing that point. You can't get there, but where is the hole? Now, I'm not asking you to identify graphically where the hole is, but when you're finding the limit, that's exactly what you're saying. You're saying where the hole is, but the beauty is I can make the question really complicated. I can make it complicated, but you still answered the question without the use of a graph. You never actually have to draw a graph to answer these questions, okay? Now, this is a good stopping point. So this is what I need you to get today. Now, if nothing else, before the next time we meet, there's a couple things. You got to watch the Algebra and Trig review because I need your Algebra and Trig skills to be at a certain level so that I can assume that you know some basic manipulation and understanding. Like with the Trig, do you know your double angle formulas and some of your simple Trig identities? I don't need you to know how to solve trig equations. I don't need you to even remember what an inverse trig function is. I don't even care about the graphs. All that stuff will come later. But the basic definitions, Pythagorean identities, double angle formulas, those are the kind of things I need you to be sharp on. With the algebra, I need you to go back and review your fundamental theorem of algebra and all of the things that go with it. I mentioned all these things in the video because these are the algebraic approaches we're going to do on a daily basis in this class. And I just want you to go back and say, okay, yes, I remember doing this kind of stuff. Yeah, there's some familiarity with this kind of stuff. Okay, so that's the way it's going to work. We're going to take a really short break, and then I will have office hours. I don't generally record the office hours. You know, that's your reward for staying on for the lecture is you get the office hours. So I'm going to go ahead and stop recording now.